Just about myself a little bit. So, Iven Mareels, I studied engineering. I majored in power systems, and at the time in power systems, the interesting bit was actually complexity. And one of the things that I was always interested in was, well, in the face of complexity, how do you make things optimally work? And that meant that systems could actually learn from their environment, how could adapt to their environment. In a power system, that happens naturally because transformers age, transmission lines age, machines change. Everything is basically, it's a living organism almost because of its size and magnitude. And so you can do everything piecemeal design, but you could also start thinking about systems that from themselves learn, well, that's an old piece of equipment, that's a new piece of equipment, how can I harmonize it and make it work? So that was where my PhD would work lead me to. And that's why I got interested in adaptive systems and self-learning systems. And once you enter that domain of learning, then it's a very small step towards, say, how do we learn as humans? And where do we learn? And then it's a very small step to start reading Wiener's book and saying, someone actually before me was thought about these questions and is willing to ask these questions from an engineering mathematical point of view. And so what is a bit of information in the brain? How does the brain represent information? How do we deal with information? How do we compute with it? And asking those questions in a way, because there is nothing that learns better than a human, at least that we know of. So that's why learning and seeing how that behavior can be transmitted into and embedded into a machine that then helps us as humans to live better. That was kind of the driving motivation for myself. And Wiener was there before me, a long time before me. And his work was basically, cybernetics. That was what he termed, and that's what he was interested in. He was really interested how do animals, how does human behavior come out of the structure of the brain, how it's a kind of, not a deterministic, but a machine viewpoint of what learning is. So bringing it back to elementary building blocks of how you can, and understanding those building blocks in the brain, of attention span, computation, representation, communication. Once you understand that, you can start seeing, well, learning must be a consequence of that, and then you can start working with it. And so that's why I started reading his work and being very interested in his work, so that I could apply it into real practical problems like a power system. I have never got there yet, but we're working on it. I believe it's important that the young researchers and engineers understand Norbert Wiener's work because of the innovation that he brought and the way that he was interdisciplinary. And Norbert in his day, together with von Neumann, together with some people from psychology, really wanted to understand how engineering and biology could actually work together. And they were trying to understand how control and command worked. And they looked at the human body, they looked at the animal world to understand how that actually use control and command, and then we're trying to learn from there to see how to do better engineering. And that topic of how biology can teach us better engineering, I think, is critically important right now. So, as you point out, neural engineering is a very important topic for engineering here at the University of Melbourne. It's getting more and more importance worldwide. And in fact, Norbert Wiener and von Neumann were some of the early pioneers of understanding neural engineering. And indeed, von Neumann wrote a very nice book about how the brain works and how you could look at the brain as a kind of analog digital computer object. And both Norbert and von Neumann wanted to understand, together actually with von Shannon, how information, how computation actually worked in the space of the brain. Both from both sides, to understand how the brain worked and how engineering could use this. Today in neural engineering, we're actually in a position that we can fulfill their dreams because to some extent they were too early. We couldn't measure things as well as we can now. They had actually no access to the real data about what the brain is and how it functions and everything. A lot of information being gathered in the meantime. We can now interrogate at cellular level how brains work. We can start building little circuits, things that they could only dream of. But they dream of trying to unravel or re-engineer the brain is still the thing that drives us today. And that's one of the things that we want to do in neural engineering, is re-engineer the brain so that we can understand and build better computers. I mean, just to think of one thing that really excites me. Your brain, even asleep, will do an awful lot of work. 20 watts, not even a light bulb. Well, nowadays, with a LED bulb, maybe yes. But a very minor light bulb does all of the computation. A supercomputer will just about get there with respect to the amount of compute power it can do comparable to the brain. 2 megawatts. 6 orders of magnitude out. That's how far we are removed from what the brain can do. That's an incredible, exciting gap between engineering reality and biological reality. And so can we get the engineering reliability with the biological ingenuity together? That would be the dream come true for me, if you can do that. We're still a long way to go. So the main limitation for the moment is still the switching in a transistor. So we're talking in transistor energy switchings, we're talking micro, say nanojoules for a single switch. In the brain, a femtojoule is roughly what we're doing, so that's the 6 orders of magnitude difference. So we're still a long way to go. If we have to shrink it even further, we might be able to get here, but then the cost goes up enormously. So this is the amazing thing, that in the brain we have a low-cost manufacturing with very lousy instructions to some extent, coming up with some really inquisitive ways of doing switching and communication that we can only dream of in engineering terms. So that's the dream that those guys had in the 1940s, or the end of the 1940s, the dream we still have today, and we think we have a little bit more technology to get closer. Yeah, so at the day, Norbert was really very much ahead of his time. When we think about the type of problems he was working on, so where he's famous for the Wiener filtering theory, he approached the problem of filtering, of understanding what information lies behind the measurement in a very clever way, using Fourier analysis, using infinite dimensional system theory. Whereas the then engineer at that time would be working with capacitors and inductors as individual components, and even building something of third order was a major undertaking, something that was not easily done. And you needed a lot of hard work to be able to do that properly. So on the one side, building things took a lot of space, a lot of time, very simple components, highly complex from that point of view, but nothing of complexity compared to what Norbert Wiener was willing to contemplate. So he jumped, just said, that's all practical problems. Let me look at the problem as it really is. Do it infinite dimensional, do it at once, do it well, and then see everything else as an approximation of the reality, of this optimality, basically, that he formulated. Yeah, that's amazing. I think that is really a lot. Same thing with Shannon. Those 3 guys, Shannon, von Neumann, Norbert, but Norbert in particular, willing to leap out in front and say, forget about all this clutter of practicalities. Let's solve the problem really, and then try to find out how we can get there. And he did that. He did it every time and time again. He used the mathematics to pose the problem neatly, then solve it, present a solution, and then also went the next step to say, how can I go from this ideal solution to something that's practical? And now he knew why it was working. He could tell why that solution worked and that didn't work, because one was a good approximation, the other one was a bad approximation of his theory. So that was absolutely amazing. And I think we all should learn from that the abstraction should be able to get away from the practical limitations and focus just on the essential. And once the essential is understood, we can then put the practicalities back in. And he did that intuitively almost. Yes, Norbert in his book Cybernetics really wanted to go the whole step, basically, and saying what will we be able to build, and how can artificial intelligence make an impact, and how can we even look at society through these ideas, basically. And that was, again, ages ahead of of anybody really. Most people didn't want to go there at all, but he had no inhibition in a way. There was nothing that was too difficult for him. He just went for it. And what he didn't know, he would read or look up or talk to the best people in the world. That's the way he was, basically. And so he brought all these theories together and started to try, how can I make a theory of everything work? And that's really what he was about with the cybernetics, really. Quite amazing. So 50 years after his death, 120 years after his birth, the conference will basically remember his work, his legacy. And at this point in time, I think it's very timely because a lot of the things that Norbert wanted to be able to do and was thinking about can actually find reality now. And so going back over the groundwork that he has done, the ideas he had put forward, and allowing us to reflect on that and see where we got to and where the gaps are. He made some amazing statements. So one thing he said at one stage was that without an information theory for feedback, we only address the trivial problems. It's only just recently that people in the control theory have come to grips with asking even the question in that space, which he posed 50 years ago. And he had the audacity to say we only would be solving trivial problems. I mean, it's quite amazing. But just now we're starting to understand how important that statement was. And I think for us to go and reflect on it and see what the actual legacy was is important. And I think that the conference will be able to do that, put him in the right daylight, put us what we have established, so how far we have gone towards his dreams, and where we're still falling short. Because still a bit of work to be done there, I think. What I would like to see coming out of the conference is that we can actually see the convergence of the field, the different fields that Norbert was actually important for. So where he brought the Macy conferences together, we had psychologists working together with information theoreticians, working together with electrical engineers, trying to make a model for command and control almost, and for how animal behavior would come about. If we could see some of that conflux coming in the conference again and see where we got in there, and again see that conflux of engineering, social sciences, and medical sciences come together, that would absolutely be fantastic. But at least to see the progress we've made, the understanding of his legacy, and the next steps. If we could summarize it at this point in time, say 50 years after his death, that would be an absolutely fantastic outcome. So one of the great challenges in the world, or the things that you hear talking about for the moment, is what we call the Internet of Things. In Europe, people talk about cyber-physical reality or cyber-physical spaces. To some extent, you want to have a network of things around you that you are actually not aware of that they are there, but they are there to help you living your daily life. And we see a little bit of that happening in the way our mobile phone can react to our space, to our place where we are, to the way we ask questions. It may remember that at lunchtime we normally have lunch. We may be walking on the street and may suggest a good restaurant around the corner to us. That type of interaction, very simple. But you can drive this much further. We can all be, our mobile phones, all of us can actually become sensors that can interact with each other. And that whole system around you has to behave in a manner appropriate to you as individual, so you can interact with it in such a way that you're actually not aware of it and that you find it natural. And those two things are difficult for computers. Natural behavior and unawareness for yourself, so that it's totally natural to you, are not part yet of computer way. When you hear a voice out of a computer, it still sounds funny. If they ask questions or they give answers, it still doesn't sound quite natural. It doesn't take you long to figure out that you're talking to a computer, normally. And the Turing Award has still not been awarded. So the next step in a way of how we interact with our environment and to optimize our environment around us will require something like an Internet of Things. Everybody seems to think that way. In order to make that work, at that level of complexity, we need cybernetics to work really well. And that's basically why Wiener's theory was so much ahead of his time. and why it's still very important to ask those type of questions, to deal with complexity in a controlled environment. And that was basically what Wiener was all about. Terry Swinovsky gave a talk here for the Graham Clark Corporation not long ago, talking about neural networks, artificial neural networks and the brain neural network, and trying to understand how artificial neural networks could behave like human neural networks, like brain tissue and things like that. So that is a part of neural engineering that is very much full ongoing work, and where on the one side you have a group of people that have come from to say, well, this is the building block of the brain. That's a neuron, and the neurons are interacting with each other through some kind of network. And they have taken that and applied it to solving simple computer science and engineering problems. And they found that that actually is a very rich literature, very rich problem in its own right, and has led to a very rich literature in its own right. But it's very much a black box approach. It's just take a circuit with a building block and some simple structure and say, what can it do? And they found out it can do a lot. What we have not been able to find is yet a structure that actually can really learn and self-learn. And there are theories around that, why and why not, but to some extent that is still very much in the future. What has happened to that is that in a way we have taken something out of biology and adopted it into an engineering problem. What we haven't done is we haven't gone back and said, well, that's what we built in engineering. What does it actually tell us about the biology? And we haven't closed the loop. And I think that is the next step that Terry is also asking himself is, can we actually now say something to the biologist about what we think this part of the brain is doing and why it should be doing that? And then let's see whether there's not a feedback mechanism that can teach each other something new. And that's really where I think neuroengineering is going to go for. Well, I can give you a simple example of why reverse engineering the brain is very important and very interesting. Take a simple question. We are humans, we hear sound. You can hear the sound whether it's from the back of your head or front, left or right. Roughly a person will resolve sound direction to within 2 degrees. You've got 20 centimeters between the two ears, right? If you want to be able to resolve something within 2 degrees with a normal wavelength of sound and everything, you would have an antenna 22 meters wide. Order of magnitude wrong. So what went wrong in our answer? Our answer, engineering, is based on a linear theory. The brain is a totally non-linear object. It uses the shape of your nose, the shape of your ears, the fact that your head is not symmetric, in order to be able to know what is back and what is front, what is left and what is right. Things that we never use in our signal processing. We would never think of these type of non-linear elements to bring them to bear. The brain does it automatically. So it actually learned non-linear objects, where in sound itself is a totally linear object. So all our theories are approached on the linear physics that is sound. Adiabatic transformation of the ear, that's what is sound. It's a total linear approach. Yet it's non-linear signal processing that gives you the sound direction, quality that you could achieve with the head. So that's why reverse engineering the brain, just that little part of the circuitry of how it uses the ears and the coordination between the ears to find sound direction, would actually help already engineering to do much better job in saying, taking the density of telephones, mobile phones, from what it is now to 10 times, to 100 times better than that, what it is now. Now that's a lot of money worth. So it's worth reverse engineering the brain just for that. Yeah, so this is kind of optimization techniques, and people use indeed artificial intelligence-based approaches, neural network approaches to solve optimization problems. I'm not a big fan of this type of optimization techniques because they're a bit like I have a hammer, so the problem I have is a nail approach. And sometimes these neural networks are extremely good in solving a particular optimization problem. But what we have not learned is what are the optimization problems that the brain actually solves? And why are the structures the brain has the way they are? And that's actually what you should answer before you start approaching any problem with a neural network. So neural networks are, in my opinion, always the right answer. And as long as we think that they are the right answer because the brain is able to do complexity, we're solving the wrong problem. So I prefer to use neural networks where they are natural, and to use tools where they belong. If I have a nail and I have to hammer it in, I will use a hammer. But if my problem is not a nail, then I will use a different tool. And that's the way I like to approach these things. So that's how I feel that you do have to know the natural environment of the problem and then use the natural tools to solve that particular problem. So systems biology is a very big topic. It is something that is very commonplace now and people are talking about it a lot. The time has come to actually think about biology. Let me make a controversial statement. Up to now, I don't think biology was a science. It was a description of what we saw in nature. But now we can actually quantify it and we can actually start making predictions about biology. And that's where I think it makes a big leap forward. And that's what system biology does to biology. It allows you to make quantitative predictions about what you would expect in nature to see if you put these type of cells with these type of structures together. That's the clever bit that system biology can do. And we can only do that now because we have enough understanding of the complexity of biology and of the building blocks of biology to start doing that. There's a long way to go. The long way to go, I would compare it to when we started to build VLSI circuits. We had the building blocks of a transistor. We knew what a transistor was. And then we now started building big complex systems with it. We are not there yet with system biology. We have some building blocks, but not all of them. We don't completely understand how they interact. But once we do that, we could actually write a computer-aided design mechanism, if you like, program, that would allow us to build with biological blocks, and integrate them with electronic circuits, mechanical devices, and use biology just as we now use physics as a part of engineering design. And that's what I really think is the promise for systems biology to engineers. For biologists, system biology has a different promise, but for engineers, that's what system biology's promise really is. How can you use life, as we know it, as part of engineered systems? Machine learning and learning in general are very interesting topics for the moment in computer science. It's a computer science question to the old age problem of how do you model the world around you. And all human beings create models of the world around them. Machine learning tries to do this in an automated fashion, almost independent of the question that has to be learned. So machine learning is critically important for understanding language, making translators, being able to help people to understand or unlock even old languages or languages that are no longer being written down, like Aboriginal languages or indigenous languages. So how do you preserve languages and make sense out of it? Machine learning can help in that space and has the tools developed to be able to do that. It can find structure where at first sight none exists. And that's the whole point of computer science and mathematics, is to endow something with a structure that simplifies your understanding and then allows you then to build with it and design with it. So machine learning has a long way to go because the problem in itself, endowing structure to something that you observe, is ill-posed. There are many structures that will fit. Some are good, some are bad structures. Which ones are good and how you make a comparison of structures is a difficult question in its own right. So machine learning, just like modeling, is a long way to go, but it's fundamental to all science, fundamental to engineering, so it has a fantastic future. So the question, how does Norbert Wiener's work interact with machine learning and artificial intelligence? Well, to some extent, Wiener was interested in artificial intelligence, as well as just in intelligence in its own right. And he wanted to understand intelligence, the way it happened, and then to indeed being able to build it. So in that sense, artificial intelligence is a consequence of some of the thinking that Norbert Wiener had, but then applied in a computer science direction. And in fact, you can see that Norbert Wiener's ideas and the Macy conference's ideas have completely independent pathways almost in psychology, in computer science, in systems engineering and engineering in general. And people have developed the ideas almost independently for a long period of time. And they've lost the insight that Norbert had at the time, that in fact going forward in one direction was losing something because you weren't informed by the other parts. And so bringing them together again and understanding that artificial intelligence and machine learning is a fantastic computer science tool, but to get its real potential, it has to talk again to psychology, it has to again to talk to biology before it can get there, where it really has to be. And I think that's part what Norbert's legacy was to us, which we have forgotten, and hopefully that we get back to it. So the question here is about how do we interface with neural tissue, in particular how do we interface with the brain. So the simple mechanism that we are for the moment using is essentially electrical stimulation. We use electrodes that create pulses, charge pulses basically, and due to that we generate an avalanche of pulses in the brain through the axons. Perfectly legitimate way of exciting a particular axon structure, but it's not the only mechanism. You can also get a reaction inside an axon because of heat, and you can do it chemically as well. And in fact, chemically is what normally happens inside the body itself. It's the pulse with which it gets excited. So you have three different mechanisms. For the moment, heat we can't localize enough. Light we could, but light then gives a similar effect as the electrical stimulation. Electrical stimulation we can simulate very precisely and very localized, very close by the axon. And so it gives us the best spatial resolution of interacting with the brain. How we actually interact with the brain, I don't think is that important, because the brain has an incredible ability to understand signals. And even if it's an artificial signal, the brain will figure out what actually it can do with it. And so, in some sense, when you look at the cochlea, that's a brain interface for the hearing, we know that what we send into the brain is extremely primitive. And yet, people with a lot of training can figure out things that we don't believe are actually part of our signal. And an example I give you, there's a concert pianist right now playing concert piano at the highest level using a cochlear implant. Most people can't even distinguish the difference between two adjacent notes on the piano with a cochlear implant. But his brain has been able to do much better than that. He can divide the two notes in 16 parts because of training. We don't know how the signal is there, but somehow the brain figures it out. So, in other words, the brain has learned to interact with a very lousy interface that we have created and given it instead of a natural ear. In the same way, whatever interface we'll have, it will be for the moment primitive, because the brain density is much higher than what we can actually build as electrode stimulation, but it will figure out how to interact with it. And so that's where I'm relying on the way that the biology will come our way as much as engineering will go its way. And I think that's why the technology in itself is not that critically important. But to be able to interact with the brain is the important bit.